One singer produces an intensity of 10 to the minus 4 watts per meter squared. That's how much energy per meter squared gets received by your ear if you're 3 meters away from the singer. Spread out over maybe a sphere of radius 3 meters, but this is what you're hearing. So if you were to have 10 singers all at that distance of 3 meters, so what do you think would be the intensity that same listener would hear? At 10 to the minus 3. So you've just multiplied 10 to the minus 4 times 10, and you get 10 to the minus 3. Hopefully 10 singers together, it's 10 times as much power. And so one singer is singing at 80 decibels, and the decibel level is measured at a distance of 3 meters from that singer. If you got closer to the singer, it would be higher decibels. So when someone complains about your party being at a certain decibel level, you should ask them where they made the measurement. 10 singers, what should be the decibel level? So when you multiply the intensity by a factor of 10, you just add 10 decibels. 80 goes up to 90. Consider a pipe with length L that is open at one end and closed at the other end. What are the wavelengths of the 3 lowest pitch tones produced by the resonance in this pipe? Yeah, that's the one I like. 4L, 4L over 3, 4L over 5. If you have an open closed tube, remember, this is what you're doing is you're forcing a node here and an antinode there. That's a quarter of a wavelength. So this whole thing would look something like that. So this, from here to here, is equal to 1 wavelength. So the wavelength is 4 times L. Does that make sense? Lambda 1 or something like that. But here, so this lambda 1 is equal to 4 times L. This is another lambda right here. This is lambda 3, I guess, from here to here. And that's going to be, and this is L over here. So I think L is going to be 3/4 of the lambda 3. So I think lambda 3 is equal to 4 times L divided by 3. You can sort of see. And then this one here, this is your lambda 5 from here to here. So lambda 5 is equal to 4/5 of L. If I go, la, okay, and then I say this, repeat the same note, but louder, la, okay, what has increased about the sound wave? Now, I probably changed the pitch there as well. Let me try it a little better. La, la, same pitch, okay? All right. Yeah, great job. That's what I meant by that. Something was happening in the pressure versus time graph. So this is a trace of air pressure versus time. Now it's the same exact trace, but I kind of just stretched it out. Now it's a higher amplitude. You hear the same sound, but now the pressure variations are just higher. This is where you do vary the pitch. That's the frequency. Okay, you guys got it. Got a couple little demos, but yeah, here's 2 screenshots showing. I have an app on my phone called Sound Spectrum Analyzer, which was a nice free app, and this was me singing La twice. I tried to sing a low B in this top graph, and then I tried to sing a C sharp a little higher. And so what you notice is that it looks kind of similar. You got these peaks, but that's the n equals 1. That's the fundamental frequency. There's the second harmonic, third harmonic, fourth harmonic, fifth harmonic. All of these are coming out of my vocal cords somehow. And they've all shifted a little bit to the right. And what's interesting, too, is that the higher harmonics have shifted proportionally as well. They've all been multiplied by the same factor. An observer is standing in the middle of the road, which maybe you shouldn't do, as a police car approaches her at constant speed, Vs. The siren on the police car emits a source frequency of Fs. So which of these statements is true? So this is, I think, what you're mixing up is amplitude versus frequency. So certainly I think the amplitude of the sound is going to get higher and higher as it gets closer and closer, because it's spread out over less area. But the Doppler shift is the same. It's just once you're either toward or you're away, because in this one-dimensional motion. The other thing that might happen, I suppose, is that there might be kind of a cosine. If you're standing to the side of the road, then actually the frequency will decrease as it gets closer. Certainly won't increase, I don't think in any case.
Okay, so let's do this question again. Again, you have an observer standing in the middle of the road with a police car approaching her at a constant speed. And the siren on the police car emits a source frequency of Fs. So in this case, is the frequency, steady frequency she observes, is it A, higher than Fs, B, lower than Fs, or C, equal to Fs?
You do hear this pretty well. Your ears are very, very good at picking up frequencies and frequency changes. So it's quite possible to hear Doppler effect. And what happens is that then it'll go down as it goes away. So if a car is passing you on the highway or something, you'll hear it go, nee. Okay, the pitch is higher as it's coming towards you, and then it gets lower as it's going away from you. What is the pitch? So the pitch meaning that frequency that you hear. Okay, and I sometimes called that F1, which is the fundamental frequency of a standing wave or something. That's going to be your pitch. And there's always going to be harmonics, 2F1, 3F1, 4F1, all these different harmonics. So what do you think? People are saying, survey is saying 100 hertz. So that's right. Basic idea is that the period of repetition of this is going to be every 0.01 seconds. There's a lot of little wiggles, but the entire pattern repeats every 0.01 seconds, every hundredth of a second. So that's the period. And 1 over a hundredth, 1 over 0.01 is the frequency in hertz, 100 hertz. So this is another way of representing a sound is instead of pressure versus time, you plot the amplitude of any sinusoidal wave versus the frequency. Because you can build up any sound as being the sum of a whole lot of sine waves of different frequencies and different amplitudes. So can you tell what the pitch is of this sound? So 50% of you were saying 130 hertz. So that's the idea, is that F1 is that the fundamental frequency. And even some of these higher harmonics have a higher amplitude than the fundamental, in the case of the human voice, but they are all integer multiples of the fundamental, and so our ear perceives that as having the same pitch, the pitch of the lowest of these harmonics. On a real guitar string, which you pluck, it's fixed at both ends. Which of these shapes would you get? Yeah, I used to think it was n equals 1, 2. That's the one you hear, right? But what actually happens is that all the modes are combined at once. And it's kind of cool. And there's even, this is like what happens when you pluck a string, and it kind of looks like that, as you would think. But what that is, that shape is actually the sum of many standing waves, all of which have this boundary condition that there's nodes at both ends. So the fundamental has no intermediate nodes. Then there's this sort of the second harmonic, which has the left half is high, the right half is low, and then it alternates with a node at the middle. Then there's a third harmonic, which has a different pattern, a more symmetric pattern. Fourth harmonic has the not symmetric pattern. If you add all of those standing waves, you can get almost any shape. And if you pluck it, you will automatically have all of those frequencies on top of each other, and that's what gives the guitar its sound, is that you hear all of those harmonics.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.